Hello, everyone. Thank you for joining today's John Bacall Colloquium. I'm Jared Heiss, the Director of Science here at SURF. A few quick housekeeping notes before we begin. Today's talk will be about 40 minutes long, followed by 10 to 15 minutes of question and answer. You can ask questions live by raising your hand in Zoom or using the Q&A button. This talk is being recorded and will be available on institute.surf/JBC, as well as on SURF's YouTube and Vimeo channels. To receive notifications about upcoming talks, visit the Connect link at the top of the institute.surf webpage. You can register for all scheduled talks at institute.surf/JBC. We now have a dedicated Slack channel to continue the conversation after each colloquium or to follow up later. A link to the Slack channel is in the Zoom chat. You're welcome to ask additional questions of the speaker or engage the broader group assembled there. The featured speaker will be available on Slack for up to 30 minutes following the talk. Now it's my pleasure to introduce today's speaker. Dr. Nhan Tran is currently a scientist at Fermilab. He completed his undergraduate degree in physics from Princeton University in 2005 and his PhD from Johns Hopkins University in 2011, working on the Compact Muon Solenoid, or CMS, experiment at CERN's Large Hadron Collider, or LHC. His research is focused on accelerator-based experiments to search for new phenomena, such as CMS at LHC, LDMX, and DarkQuest, and the interface between artificial intelligence, electronics, and instruments to advance science. Tran is a recipient of the URA Tolostop Award, the APS Henry Primakoff Award, and the DOE Early Career Award. Now it's time to turn things over to Dr. Tran to learn about exploring the cosmos, the Genesis mission, and AI in particle physics.
All right. I assume everyone can hear me? Okay. All right. So, yeah, first, thank you very much for the opportunity to come and talk to everyone here about the interesting and so very timely intersection of AI and physics. All right. So first, just a little bit about myself. If you don't know me, so I grew up on the CMS experiment. As a PhD postdoc scientist. I'm also interested in exploring other fixed target experiments such as LDMX and SpinQuest for looking for dark sectors. My current position at Fermilab, so I lead the AI program at the lab. It's something that cuts across the whole organization. And then I also have a formal role leading the intelligent microelectronics system. So that's kind of my interest in AI electronics and computing and physics. Yeah, so something else about me. So I've also been involved in this organization called Fast Machine Learning. I'll talk a little bit about this today. And then just kind of as an aside, maybe as a smaller thing, but something that I did a couple of years ago is I co-chaired a DOE Office of Science AI roundtable on user facilities. And I bring this up just because I think it was an interesting opportunity also to learn about how other fields of science, so if you don't know these acronyms, it's okay, but things like biology, material science, fusion, to just kind of learn about how they're also using AI in their domains. Okay. All right. So let me kind of do one other sort of prologue here. So, I mean, AI is a very timely topic, of course, and I think there's an opportunity to do things fundamentally different. I think the questions are still out if we need to do something fundamentally different and if we should. This talk doesn't really address societal or ethical aspects of AI, mostly for time purposes, is something that's another huge topic. But I don't want to make it seem like it's not part of the discourse. And then, so from my point of view, this talk sort of assumes the optimization of, how much science can we get out of a fixed set of resources. There's lots of literature out there on AI and physics, and so there's a link here at the bottom to this great resource of folks that are kind of keeping an overall view of AI in the field. Okay, so here's the outline of the talk. So I felt like it was a good we should talk kind of just about the evolution of AI in the past 10 years or so. It'll be a super quick overview, but kind of, I mean, without understanding the technology, I think it's hard to understand exactly where, the intersection of it with physics. And then the second part of the talk is going to be about that intersection, just all the multitude of places where we can apply AI. It's a kind of a collision of two domains, and so I wanted to be able to talk about some of the buzzwords that are in AI and how it relates to science in a way that's the sort of common language. I wanted to give a couple of examples. So this is where I'll get a little bit technical, but kind of a few examples of where I see things being applied. And then finally, just a few words at the end on the Genesis mission. Okay. So first, the evolution of AI. There are first a word on terminology. I think people use a lot of different kind of uses the words interchangeably, and it's sort of a convention. This is a definition that I like, where AI is the overarching term. Machine learning is a certain aspect of AI, and then deep learning is kind of what has driven the most recent boom. And even this sort of definition also does not really include the latest kind of uses of the term AI, but for the purposes, I'll call it generative AI or Gen AI. That's one place that the people also kind of use these terms for the sort of latest boom in large language models and agents. All right, so just to talk a little bit about the rise, I think there are, I would say, four main reasons, at least in my head, that this kind of came to be. Within physics, we've dealt with very large data sets for decades, and I think this has really caught up with the rest of the world in terms of whether it's the internet, self-driving cars, Industry 4.0. There's been a necessity, of course, to be able to digest this just massive amounts of data. At the same time, there's also been an evolution of hardware. Obviously the GPU has been a big driver of the technology, and so kind of just thinking about how you're able to do all of these massive amounts of calculations, which I'll talk about here in a second, in sort of a tractable amount of time. And while we have the GPU certainly is the driver right now of where things are going, I just wanted to make sure people are, there's a huge amount of technology and investment going into developing that next generation or current generation of compute. And I'm just giving you just sort of a vignette of a number of different other companies that are kind of developing AI specific hardware. And then of course there's also the tools, the making all of that hardware accessible to be able to train new models and kind of make this much more broadly accessible. So things like PyTorch and TensorFlow, and JAX, which is a differentiable framework. But then also the sort of lower level languages, for example. I mean, one of the big reasons I think why the GPU has been so prominent is just because of the availability of CUDA to map algorithms directly to the hardware. Okay, and then finally data. This is the big driver for AI. And just one nice example of this is ImageNet. I mean, this was what kicked off the computer vision boom in the early 2010s. And I don't know if everyone remembers or knows the huge amount of effort that went into developing this data set, right? More than 14 million images labeled into 20,000 categories, all hand annotated, right, by a group of people. So, this is kind of what really kickstarted everything from the data point of view. Okay, so let me just start with computer vision. This is one example, just kind of how these deep neural networks work, where you're able to kind of build these layers of processing that goes from that looks at different parts of uh, this image and passes it through to be able to provide an input and an output. I'll say that, even though this is a hugely this was the first big boom in AI, even this algorithm, which is very compute intensive, was already a big step forward in terms of reducing the computational complexity over traditional fully connected layers. So thinking about how architectures for AI architectures map onto your input data kind of enabled this first big boom. And of course, these models are just getting significantly more complex. I mean, this is even in the late 2010s, just the state of the play for vision models in terms of gigaflops, so operations, billions of operations per second, and the number of parameters in these models are so in the hundreds of millions, right? So you can see just the sort of going in that first decade, just the complexity of these models kind of scaling also with the compute and the tools. And then, of course, that brings us to natural language, another sort of really critical modality, data modality. And just a couple of seminal papers here, so attention is all you need. So there's a lot of work in natural language processing, obviously, before this as well. But this architecture of transformers was something that was easily able to scale onto the hardware than previous methods. So again, this is kind of showing that interplay between how algorithms, hardware, and data all work together. And then, of course, there's another paper, maybe not as well known, but I think is coming up a lot now, is scaling laws for neural language models, and this is kind of showing just the power of being able to scale these models and just keep making them bigger and seeing the performance continue to improve. So yeah, there's a lot of sort of big things that have happened in the last decade here to kind of get us to the place where we are now. And of course, large language models being the sort of the latest generation of the AI boom. And I think everyone is familiar with this, ChatGPT or Claude or whatever, just showing this emergent large language model behavior, which is really striking, synthesizing knowledge across all of its training data and so on. And these models are getting really, really big. Again, now in the trillions of parameters. And so this is kind of then driving the next also boom in hardware and data centers and things like that. So, hopefully this was kind of like a quick but sort of walk through the past, but can get you up to speed on where we are with AI. Now I want to kind of talk a little bit about some of the challenges that I think are coming or we're already here. So one thing, for example, is of course that the field is constantly changing, right? So even with these agentic workflows, so LLMs working together. This has changed significantly even within the past 6 months, right, with the introduction of Claude. Now, one thing that I always, I think we always need to be aware of is that there's this kind of very sort of I don't know, well-known memo from actually 2023 talking about sort of the impact of open source also on these different on these tools. So there's always a concern that how connected or how dependent are we going to be on these closed source frontier models. And I think a big part of this ecosystem that we have to kind of continue to monitor are the open source models. Things like Gemma 4 came out not that long after this recent spate of Claude models. And then there's even newer models, for example, even a couple of months ago, that kind of have shown similar performance to some of these frontier models. And I think that's going to sort of be important to pay attention to in terms of what we will have access to a sort of an economically viable way, for different scientific applications. Okay. Let me go on to talking a little bit about intelligent systems, a little bit more broadly. So, whenever you use ChatGPT, for example, you get this disclaimer: ChatGPT can make mistakes, check important information, so this is something that you have to verify when you're using the tools. So that being said, I think this evolution of moving AI more into the physical world, is coming, or it's already here, depending on your view. And so, it's not just interacting with the chatbot or even in the digital domain, right? I mean, there's the full ecosystem from, Internet of Things, sensors, to edge computing, all the way to the cloud and the data center, right? And this is something that I kind of wanted to stress, is that full system view of how we're using AI. So for example, I mean, there's this great example of AlphaFold, for protein folding, and just the change that it made in terms of transforming that field, using AI. And so while this is, I'm not taking anything away from this advancement in this work, trying to thinking about how this advances the field as a whole, right? So now you have all these capabilities for sort of more rapidly developing high fidelity hypotheses. In the end, you still have to test these things, right? You still have to go to the wet lab. And so, thinking about the full scientific life cycle, and then, where the bottlenecks kind of shift to, with AI, that's really important to think about. And so, the dream here is that you're able to develop new hypotheses, but then you have to be able to test them in the lab as well. And so the dream is here to have, these autonomous self-driving experiments as well. So this is kind of why I like to evoke. It's not just the agents, but also the sort of autonomous systems. And then if you kind of translate that into the scientific world, I mean, the challenges are just much harder in certain dimensions. So, for example, if you're trying to now do sensing in, microns of spatial resolution, or nanosecond resolution, or in very high radiation or low temperature, this is kind of the challenge that we have on the science side. Yeah, and then finally, also thinking about energy, and systems, right? I mean, all these things are running on GPUs, a kilowatt scale, but obviously we're powered by something that's a lot more, or a lot less energy, uses a lot less energy. And so thinking about, what this means in terms of full systems, where does processing happen, in the eye, in the brain, on the edge, in the cloud, to build full systems, is something that's really, really important to also kind of keep track of. Okay, so yeah, so this is kind of thinking about those challenges that come when you start to build full AI systems. This is a slide I adapted from Roboticist, and just is kind of just summing up the challenges, right? Agents are only in the digital domain. Okay, now maybe less so on the number of tasks at a time, but there's a lot that goes into task orchestration, varying timescales, changing environments, different data modalities. Then you're thinking about real-time requirements, and then of course robustness and reliability. So robustness in the physical world, where failures can be much more catastrophic and immediate. And then finally, while this generation of LLMs is trained on a ton of data, right? I mean, the physical world is much more complex and dynamic, and very data hungry as well. And so I always like to tell a story about how the impact of trying to build world simulators. And I visited a while ago a self-driving car lab, and kind of talking to them about the simulators that they use, and one of them being, for example, video games. So if you're developing self-driving cars, actually you could think that video games like Grand Theft Auto would be kind of a valuable tool, because you just think about all the effort, and years of knowledge that went into developing these sort of world simulators. Okay. So, with that first part, I really wanted to talk about just the kind of state of play of AI and kind of where we are, how we got to where we are. And now I want to kind of shift gears to talking more about the AI and physics. Um, okay, so let me just kind of start with a common language. I think I've done a number of projects which kind of span AI and HEP, and actually I feel like um, the challenge is always when you're working with people from different domains is language, being able to translate how people think about different problems. So from the sort of value proposition point of view of physics for AI, I think that there's why are people kind of attracted to work together? There's kind of four big things in my mind. So one is the facilities and the experiments, right? I mean, we have these just very complex experiments that we have to operate. They're in extreme environments, and it's just just the complexity and richness of the problem is very valuable and interesting. We have this very deep domain knowledge. If you think about kind of where our knowledge is encapsulated in the field in terms of our simulations and our theories, I think that's a critical component to being able to deploy um, AI, but also kind of a constraint that's interesting for the AI community. We also have hard constraints in terms of trustworthiness, robustness, and so being able to test those for AI is very valuable. And then especially in our field, data. So data, I mean, we have uniquely massive data sets. They're very rich, high fidelity with our data and our simulation. And so this combination of these four things is kind of a unique value proposition for physics in the field of AI. All right, so kind of let me, I kind of showed this kind of series of slides, often just kind of like kind of catch people up or kind of make sure we're all talking about the same thing when we talk about the sort of scientific or physics process and where I see people using AI to cross the full life cycle. Um, so let me first start with sensing. I'm actually going to talk about this in a little bit more detail in a little bit here, so I'm not going to go too much into detail here. But sensing itself, using AI to process data in real time at the source, that is where you can get basically fundamentally new types of data or better data, and that kind of just changes the way that we're able to run our experiments. Then there's the sort of control or optimization of the experiment. It can happen at many different time scales, whether it's calibration or control or monitoring or triggering. You have different scales, closed loop, human in the loop. These are all very critical to getting at the best data out of your experiments. Um, and there's lots of different AI enhanced control methods, such as reinforcement learning, which are able to unlock new capabilities. Okay, going on. So simulation obviously is a huge part of the whole endeavor. This can happen at all different types of scales. But the point here is that we have very expensive simulations in physics, and so using AI enhanced, sometimes they're called digital twins or surrogate models, can be used to improve or accelerate the performance or the things that we can get out of our experiments. So, for example, you can accelerate synthetic data generation very rapidly with surrogate models, so-called fast sim. Sometimes you just have data and you don't have a really great simulation, or you have a sort of a poor simulation. You want to be able to enhance it with data, and so that's where surrogate models and digital twins can also help. And then this ultimately can enable more efficient facility operations or deeper insights into your experiments. And I also wanted to kind of call out here theoretical insights, models of the universe are as well kind of, at least in this picture, kind of fit into that scenario. So when you test new physics scenarios, being able to do this, comparing AI to using AI to compare um, new theoretical models with experimental results is kind of a big part of what we do. Okay, so then this is the sort of classic use case for AI in physics. It's this reconstruction. You have these high-dimensional data, then you try and do things like classify events or optimize analysis cuts and so on. But of course, this is also kind of evolving in the way that people think about it. There are a lot of contemporary thrusts here in terms of interpretability. I was always asked, why is the AI algorithm working better than sort of traditional rule-based algorithms or whatever was used in the past. There's also things, I mean, as these algorithms get more and more complex, you have to understand their robustness. Can they adapt to different detector conditions, data sets, and so on? And then kind of this concept of generalizability and self-supervision in terms of foundation models, being able to, pre-train a model on a number of different on a large data set, and then being able to fine tune them for different tasks, or just be able to use them generally for multiple tasks. This is another sort of contemporary thrust. Okay, and then finally, taking that high dimensional data to ultimately estimate physics parameters from data in theory. Some buzzwords here are simulation-based inference and uncertainty quantification, which is happening at high dimensionality. And then that's just the sort of data processing pipeline. You can also then use this to improve design of the next experiment or the next analysis. And so this is where things again like digital twins and surrogates are super important. There's another sort of contemporary thrust here in differentiable surrogate models that can you can rapidly optimize design and search with this differentiable surrogate models. Okay, so hopefully that gets, sorry, I kind of went kind of through the full sort of scientific stack here, but I think it's important to kind of have this global view, because if you have AI that's able to improve a certain part of the stack, then the bottlenecks move from place to place. And so understanding where people are doing things across, where AI is being applied across the full stack is super valuable. All right. So let me just give a couple now, like technical examples, so that you kind of get a sense of a little bit more of me, and maybe some examples that I think are directly applicable. So the reason it's called extrema, so I'm going to take the two ends of the spectrum. So I'm going to start at the sensing part here, and then also talk about the entire endeavor and the way we use agents across them. So I wanted to kind of do a little deeper dive on this sort of sensing and fast machine learning for science community that I'm a part of. The vision statement here is that scientific discoveries come from the ideas, but then also to be able to test nature at new scales, right? So either it's finer spatial resolution or temporal resolution, and so to unleash the full power of machine learning in science, we really have to be able to embed it into our scientific process and into our instruments and our detectors. And so this is a kind of a plot that I show fairly often, which is kind of looking at certain tasks across a number of different fields, but kind of pushing the envelope in terms of speed and data rate. So there are challenges and tasks in physics, but also in material science or neuroscience, beam control, all these sorts of things, where you might have to go at nanoseconds or microseconds, and the data rates are huge. And I think this is a challenge that requires a number of different domains, AI researchers, computer architects, domain scientists. But the challenges here, they're fun and exciting because they kind of push the envelope in terms of technology. So, you might have things where you have to do tasks on mobile devices or Internet of Things. So, on the sort of millisecond range, but to be able to do, processing at that, microsecond, nanosecond range, to be able to do sensing at the scale of nature, I think that's a really powerful paradigm. So let me just give you an example. I grew up on the CMS experiment. If you're not familiar, this is one of the two general purpose detectors at the Large Hadron Collider, colliding bunches of protons at a rate of 40 megahertz. Right, so you have a 40 megahertz detector, a billion detector channels, and so the data rates are they're just massive, right? So you have data streaming off this thing, sort of comparable to the global internet traffic bandwidth. And then you have this very complex pipeline of data processing, and it goes from on-detector specialized chips, which are able to zero suppress and even do lossy compression of the data. Then you pass them on to FPGAs that have to do processing on the sort of microsecond scale. And then you pass that data, which has then been filtered down to hundreds of kilohertz, to an on-site CPU or GPU filter farm, hundreds of milliseconds or so latency. And then finally, you get order, 5, 10 kilohertz of data, which you can then save for data processing later. And even the size of these data sets are exabyte scale. And so to get the most out of our data, there are opportunities to deploy AI at the frontmost, the sensing part of the detector. So you have these ASICs and you have these boards which have processing engines on them. And we're, for now several years working on trying to deploy AI in these chips, in these programmable logics, to be able to do be more efficient in collecting data. And so while I'm talking about one of the most extreme examples with the CMS experiment, I think that this paradigm exists generally in science. So you have this is my sort of cartoon of an experiment. You have a sensor here. You have some analog signals. It could be a pulse. It could be some frequency domain signal, some Bunky signal. You then digitize that with some signal processing algorithms. Then you do data reduction and then you save to disk, right? But if you take this paradigm and then you say, well, okay, let's say one sensor channel is 10 bits of data, and then I want to, take data at 1 megahertz rate, so a million samples a second. And then now this sensor has 100,000 channels, or this array of sensors 100,000 channels. You're quickly up to a really big data rate, so terabits per second. And this is the challenge, right? So, if you just save everything, there's too much data, and often it's too late to be able to do any sort of actuation on your experiment. And so the whole idea here is that we embed more intelligence in this data reduction or control pipeline to be able to, improve the capabilities of our experiments, get more out of the data, and so on. All right, so this is work that I've been it's a project that I've been involved with for a number of years. It's called HLS for ML. It helps to kind of take models that we want to deploy, in our experiments, and then be able to embed them into our real-time processing chain. Usually in terms of these specialized computing hardware paradigms like FPGAs and ASICs. So this is the tool that we've developed. It makes sort of this process much more accessible for domain scientists, not just sort of very advanced electrical engineers, and be able to work together to kind of embed AI models into our experiments. And this whole process, I mean, it's been really successful. We have a number of users, and you can see these types of things being used in research and even deployed in experiments. And I kind of want to just talk through the process and kind of where we are with our latest kind of research. So this process, right, if you think about it, right, you have some physics requirements. I want to be able to search for this signature much more efficiently. Then you think about the data representation, and then maybe you want to optimize some algorithm. And then on the other side of this co-design loop, you have hard constraints. Do we have to do this in a certain amount of time? What is the sort of rate at which we have to ingest data? Is this operating in a high radiation environment, cryogenic environment, and so on? And then there are all these steps that you have to do, all these knobs that you can tune. You might quantize the network. You have to think about how to represent this quantization. You might clean up the network or make it more efficient through something called pruning or sparsity. you decide the microarchitecture of these algorithms, then you have to validate that it all works on the chip and so on. So this is a very laborious and time-consuming process, even with a tool like HLS Fermel. And so, now working on this for several years, we're kind of now trying to take advantage of some of those agentic tools to be able to make this even more rapid in terms of experiment design and algorithm deployment. So this is some very recent work we've done on using surrogate models to accelerate this whole design process, which we call the Surrogate Neural Architecture Co-Design Package, or SNAC Pack. The idea here basically is that in a traditional workflow, right, even with these tools that make it accessible, you might have some idea for neural network architecture, and then you try and implement it in hardware with maybe tools like HLS/ML. Then you have to wait, for these tools to run for minutes or hours or for a very long time. Then you find it doesn't work. Then you retrain the model. Then you do it again and again and again. And this optimization can take weeks or months. And so what we've done is we've kind of taken a whole corpus of existing circuits and then build a surrogate model around it so that it can do this sort of fast prediction of what the model looks like in hardware very rapidly. And then this kind of makes this sort of minutes or hours long process very rapid, because you just then need to do the inference of the surrogate model. So this is an example of accelerating workflows with surrogate models. And so then we've been able to also bolt an AI agent onto the front of it, so you can talk to this sort of optimization assistant, and then be able to do quick searches for design, very rapid design, and searching the design space very rapidly. This is actually something that we've done as a part of the Genesis mission here. So being able to demonstrate this process now running on a supercomputer. So this is a process of kind of trying to find the most optimal qubit readout algorithm that has to be run in, let's say, under 200 nanoseconds on a chip. And now this is doing some Pareto optimization of how fast the algorithm runs, the resources on the chip, and sort of its overall accuracy. And something that took us hand-tuned months before can now be done in 15 minutes on a supercomputer. All right, so let me just give one practical example. This is the axolotl algorithm, runs on CMS. And the idea is kind of in that same vein, where we're doing this real-time processing pipeline. We we have this whole triggering farm, which maybe looks for the most interesting events that happen, kind of as I was discussing before. But you never know if there's something that you're just kind of blind to, and so we want to be able to just look for things that are anomalous in general. And so this is a traditional autoencoder structure. So it's an anomaly detection algorithm. So basically you train it on real data, and then you look to see if there's just any events that are just abnormal. And then we can kind of save this kind of population of strange events, strange collisions, and look at them after the fact to see if we're missing anything. So the algorithm itself runs only half of the autoencoder. It takes, the kinematics of jets, electrons, muons, photons, and missing energy. It inputs them into this neural network, and then it looks to see if there are any anomalous events. This algorithm has to run on hardware. It's ingesting the full 40 megahertz rate of the LHC. And it runs in 2 clock ticks of the LHC clock, 15 nanoseconds, in an extremely small amount of chip resources. This thing exists in hardware. This is the algorithm on the chip. This is just the transistor layer out of the chip, and just showing this thing being implemented in the actual readout electronics of the experiment. And there's I had a link, sort of a reference on the previous page. You can go and learn more about this, but the short story is that for, there's just so many different possibilities in new physics at the LHC, and so this anomaly detection algorithm, for certain sort of uh, um, different possibilities of new physics, you can get actually 10x increase in signal efficiency, right? So, for an experiment that runs for decades, you may, with this bump in signal efficiency, this can really accelerate the potential for discovery. So this is another great example. This is a great example to me of kind of how how AI sort of. Oh, the lights went off around me. Um, AI in the signal processing chain being able to improve the performance of different experiments. And while I did this one example, this need for speed can be used in lots of different places. For example, beam control, being able to produce higher quality beam to surf for the Dune experiment, and also to do things like supernova detection for Dune. Okay, so let me do one other small technical vignette, and then I'll wrap up here. So the other extreme for me is agentic operations. So I showed this picture here, AI to physics translation. One thing that we can do to sort of optimize this whole process, of course, is that there's just a ton of say tacit data that just gets sort of accumulated through this decades-long scientific process, whether it's logs or wikis or indicos or Slack chats and so on. So the question is, how do we capture all of this HEP-specific information to be able to, account for knowledge lost, automate workflows, and just ultimately save time and resources. So this is a great place where you can use agentic AI. And so, I always showed this plot here, just talking about the ultra fast side of things, but I always also like to remind people that these are also decade-long campaigns. And so, my memory might last for days, weeks, months, but to be able to, how do we capture the other extreme of this across, the 18 orders of magnitude in time that these experiments exist in? So let me just give a really quick example. I think there's lots of examples of this happening within the field. This is on a really nice slide that one of the folks here at Fermilab is working on. So this is Hayden Hoschauer. But I like this slide because it kind of emphasizes how important that we are in this process, right? We're only as good as the data. These tools are only as good as the data and how we're able to search them, right? And as the domain experts, we know how best to efficiently extract information from all of this, these logs or databases or documents and so on. And so, he's been working very hard on making sure that we do the right semantic retrieval, based on, our domain knowledge. And so this is a big part of, this, using LLMs to extract information from our sort of documentation and these different databases. So there's a nice example here. So within the accelerator complex, they use I think the name is updated now, but it used to be called Logbot, where it can help operators to reduce accelerator downtime. So you can say, oh, I looked for this. Something happened, do I need, can you help me understand or diagnose this problem? It has access to years and years of prior logs. So for example, it might say here, here's an example of, potential root causes, but then it also points you to an old elog entry, where, it found some similar diagnosis, right? And so this is already kind of being used in the control room here at the accelerator complex to help operators, is a really powerful tool. And of course, you can imagine that this is useful in a number of different areas. So using scalable platform. So I think it's important that we need scalable platforms for serving these agentic workflows as well. So this will kind of get me also into closing up here a little bit on Genesis. Okay, so yeah, let me close here. Talking a little about Genesis. There's the executive order at the end of last year, launching the Genesis mission here at Fermilab. There was this town hall a week later, and so we had a sort of pack house following the sort of initial announcement of this of the mission. And I'm just taking some of the public material here, right? So this is the page, genesisenergy.gov, which is a national mission to accelerate science through artificial intelligence. And it's across a number of different areas, the thrust being, discovery science, national security, and energy innovation. You can go to the page, you can find a number of these different thrusts. And I just took a snapshot here of the discovery science one where, you have quantum algorithms, particles, up to molecules. So just a couple of different highlight areas. So maybe to give you a little bit more of a snapshot and kind of structure, at least into how we think about the Genesis mission. I don't know how much you're following these, but they all have these different parts of the platform have different names, American Science Cloud, Model Consortium, and so on. But ultimately, what it looks like is you have your data. You have a compute and storage stack, you have a models pillar here, and then you have a number of different applications. And so that's kind of the view, right? So, you have your laboratories and then your user facilities, which is the sort of crown jewel of the DOE complex. You have your supercomputers and your scientific data sets. And that's where you're then sort of kind of working all together to develop this full platform. I will say as being a sort of part of this for the past, better part of 9 months, this has, I think, for me, kind of seen at a different scale how national labs, industry, and academia have been working together. Obviously, the story is still being written, but it's been interesting to see sort of traditional barriers being broken down in terms of collaborating. And then ultimately, we have the drivers, the mission drivers, and so there was this thing that came out several months ago on the National Science and Technology Challenges. Um, and it's great to see kind of you can see physics here represented in terms of one of the big national science challenges. Okay, and then finally, I just want to say a little bit about, kind of how we view this from the Fermilab point of view. Again, we are a physics laboratory. So thinking about, kind of our value proposition in terms of those facilities and experiments. These are just the complexity of the accelerator complex, the detectors, and so on, but also the expertise across the scientific life cycle. Thinking about, the people here, right? I mean, from design, control, operations, simulations, theory, insight, and so on. On top of this, we are building this thing called the Fermi Data Platform, which really, leverages our capabilities in being able to serve data for the physics community and making it more broadly available. And this is really the sort of foundation on the basis on which we then build, of course, state-of-the-art algorithms for our scientific discovery areas, whether it's high energy physics, accelerator beam physics, quantum systems, or microelectronics. All right. So one last slide. This is a really, it's an exciting but also uncertain time. But AI is, I think the big technological leap of this generation. I hope I've kind of emphasized to you, the importance, I think, of considering the full life cycle of the scientific endeavor in terms of where you want to be applying AI. And I think we are still the critical resource. Data, high quality data is still the foundation, but we should maybe expand the scope and diversity of the data that we collect, not just the scientific data, but also the data that comes in to the scientific process itself. And then, of course, the knowledge that is encoded in our simulations, models, and expertise. The story is still being written on Genesis mission, but I think it is an opportunity to fundamentally shift how we do science and bring expertise together in an unprecedented way. All right. Thank you.
Very good. Thank you, Dr. Tran. Let's see if we have any questions? That was a fabulous talk on a very timely topic, as you mentioned. Do we want to unmute? I think you would have to do that. Oh, there's a Q&A. Michelle, we'll unmute you. You can ask your question. Go for it. Michelle?
Yeah, sorry, can you hear me?
Okay, let me go ahead.
Perfect.
Oh, okay. Michelle was curious about the next generation of physicists coming into the field. How are universities incorporating AI and machine learning into physics program now? Are new graduates coming in and getting those skills, or are early career researchers mostly learning how to use these in their job? And more broadly, what are you seeing in terms of the younger researchers and how they feel about using AI as part of their research?
Yeah, that's a great question, and one I kind of punted at the at the beginning of the talk. Yeah, in terms of education, I mean, so obviously I'm at the lab, so I don't, I'm not developing curriculum myself, but we have lots of university collaborators, and just talking with them, I know that there are lots of kind of new courses or curriculum that are being developed in terms of using machine learning and data science with data science in physics. I have a number of collaborators that I know are teaching courses like that. So that's really great. I think that beyond that, there are just a number of sort of younger researchers coming in, or the next generation coming in, and just with those skills, and just kind of looking for them in terms of classes or availability, even at the undergraduate level. One thing I'll say is that, the technology itself moves so quickly. And actually the early career folks are the ones that are, I think most in the best place to understand how to adopt those. And there aren't even courses on this, right? I mean, this is things that are changing in the 3 months or 6 months. But that sort of these advances are coming because of, the undergraduates, graduate students, postdocs who are adopting the tools, and they're teaching us about them all the time. That being said, you're right. I mean, there's also a pushback in terms of using AI as a part of their research. I think there's bimodal sort of aspect of it, where I think even though some of those early career folks are the most quickly to adopt, they're also the ones that are most passionate against it as well. And that's certainly understandable, whether it's societal or ethical impacts as well. So, yeah, we see both. We see both ends of the spectrum, and I would say they are the most extreme, right? So they're in both adoption and in reservations and concerns.
Good. Couple of questions in chat. Let's start with what is the biggest challenge in implementing AI ML in FPGAs?
Yeah, I think I mean, this is kind of our natural evolution, right, in terms of using AI in FPGAs, that we basically, let me see, I can do this. I can traverse the slides rapidly enough. So we developed this tool, HLS4ML, and before, I would say, used to develop an algorithm, maybe write it in Python or C, and then work with one of the engineers on the project to kind of then translate this into lower level RTL, so VHDL or Verilog languages. Or if you had a really sort of outstanding student, they would be able to learn the languages themselves. With the introduction of these tools, like the HLS stands for high level synthesis, you can write low level logic in languages like C or Python. This has made that easier. And then when we made these tools available, then the bottleneck shifted, not from being able to program the algorithm, but be able to then wait for, to be able to see how things are synthesized in the hardware and so on. And that's why we ended up developing tools um, like this model, like Snackback. So maybe, then we saw the bottleneck shifting to doing, to this problem. The current challenges I see still, I don't know. I mean, the implementation to me is not so hard anymore. I think it's kind of the um, keeping up with new ideas. And so this is where actually you're seeing coding agents also having an impact. A lot of people are exploring coding agents for low-level hardware optimizations as well. So that I wouldn't say it's necessarily a challenge, but it is a big trend to see. There was a lot of, I mean, if you think about um, implementing algorithms into hardware, it is basically a language translation challenge, coupled with physical constraints. So I think that's where we're going to see things going, right? And there's a lot of work on sort of AI for design automation.
Good. Another question in the chat from Chad. What is the role of AI in theoretical physics? Um, Ideas that might exist mathematically, but are sort of beyond our current understanding of physics.
Yeah, so I'm not a theorist, but we have a number of excellent theorists here at the lab, and then also across the community, and just being able to communicate with them, hear their challenges. Um, I can give you a couple examples. Again, these are, to me, they're secondhand because it's not something that I work on directly. Um, but one thing is, and we have some projects here about basically accelerating the loop of being able to put new theories or our theoretical tools into the experimental simulation, run the workflows, be able to test um, things more rapidly. So, if you have some new BSM model, you can get it into the experimental simulation much, much more rapidly with agentic tools. I think on the sort of pure theory side, I think is a really interesting evolution that's happening now. I don't think the story is fully told yet in terms of being able to test new ideas much more rapidly. There's a nice little vignette that one of our theorists tells about how he had some crazy idea and he would never give it to his student to try because it would be 18 months lost and then not necessarily good for their career. But now it's potentially something you can check within a couple of weeks to see if it's even viable as a path. So that might be along the sort of lines of the second question that you have.
Good. All right. A couple questions in the Q&A. First one about making the data more available, and then a question about the democracy of the data. Who would have who would have availability to the data? Is that just academic institutions or the public at large? I don't know if you had thoughts or comments on the direction of that topic.
Yeah, so there's data more available to the community or to the collaborations. I think that is a kind of a big bottleneck that we have now, right? I mean, we have Twickies and Mattermosts and DuckDBs and Indicos, and they're all different places, right? And if you kind of being able to build a platform that can integrate all that information does not exist. And I think even I had an interesting conversation with someone from industry yesterday about, what does that even look like? I think the traditional IT solution for that would be a big data lake house or something like that. We put everything all in the same place. But maybe that isn't needed anymore, right? With the way agents can grab data from different sources. Of course, we have to then be very careful about data provenance and accessibility. But I think this is also still evolving very rapidly. And then whether or not this is available to the public at large versus the research community, again, another very difficult topic. But data owned by experiments. I mean, we have policies in place for for data from collaborations and when they become public. So that to that extent, that data, we would follow those data policies that already are in place. It just is a lot more expanded in terms of the scope of the data that people want availability to.
I know Dune has grappled with some of those questions as well.
Yeah.
Maybe one question to wrap things up in Q&A as well. Have you noticed any of the large language models influencing, maybe enhancing the exchange of ideas in scientific fields?
Um, it's it's hard to say, at least to me, if it is the impact of LLMs. I guess so. I mean, the accessibility to other fields is the barrier to other fields is much lower now. So in that sense, yes. I mean, for sure. Like I was trying to learn about a specific topic on fabricating chips, and I was able. I felt like I was able to get all my questions answered very rapidly in a way that was not possible before. So yeah, I actually now that I think about it, yes, certainly. The reason I was a little bit hesitant to say that is also because at the same time, AI has brought many fields together as well. So I don't know if it's the impact of LLMs or just the impact of AI in general, but probably both. Yeah.
Good. All right. Well, let's go ahead and wrap up. Thank you again, Dr. Tran. A
Thank you.
reminder that today's talk will be available to view and share on institute.surf/JBC, YouTube, and Vimeo. Next month's John Bacall Colloquium will be virtual only and will be held on September 9 at 9 a.m. Mountain Time. The topic, the Nemesis Experiment, with featured speaker Dr. Vladislav Trotska. As a reminder, please join us on Slack right after this talk to continue the conversation with Dr. Tran and others. The link is in the chat. Finally, we value your feedback. Please take a moment to complete a short survey that you'll receive in Zoom and by email. Your suggestions on future speakers and topics help ensure that this series remains relevant and useful to the community. Thank you again for joining us today.